Dr. Takashi Ikegami is a professor at University of Tokyo known for his pioneering work on complex systems, artificial life, and emergence of intelligence and consciousness. Professor, thanks for joining us.
Thank you very much
Welcome to
for
the show.
inviting me. Yeah.
Okay, so let me ask you this. What is death?
Oh, we begin with a very difficult.
Very difficult question. We're going to start with this. I mean, what is life? What is death? And maybe that's where your interest is, maybe, or...
Well, yeah, I'm very interested in this. Yeah.
Okay. I mean, obviously, it's you have to have both to understand the concept of life and death.
Right.
I mean, it has, and death is definitely a necessary condition for life, and life also, I guess, unless you decide to live forever, death is. But again, for us, death is inevitable. But for some, say, organs, or I don't think organs. I mean, do organs die, or do cells die? Organs die. But what does that mean to let's say, when you think about consciousness and being sentient? What does that mean?
Yeah. Well, actually, my master thesis was related to that, because once people say that you're dead, but your brain, your cells, are still alive, connecting with other cells, right? And within the cell, those, the metabolic cycles also still alive, right? So the death is more about the scale dependent. So once you see organ, it was died, what was still alive, your cells still alive, but the individual level is dead, right? It's not functioning, right? So I think there's no such things like once something is dead and everything is not functioning. Right? So I was interested in that too, but then I studied immune network. Immune network is a chemical network, right?
Yeah.
So neural network is a distinguish between, say, mental self and non-self. But the immune system distinguish material self and non-self, right? So which one is material self and non-self, right? Because once you touch some plastic, something that some people are very allergic to plastic or metal, right? But once you take it very much, right, then that becomes your self part.
Okay, you have like two systems. One is the immune system, the other is the neural network.
Yeah.
You have two systems, and
Yes.
you're saying that they're different.
That's right.
Immune system is more fundamental or rudimentary, whereas neural network is more like kind of like LLM.
Yes, that's what I think. Yes.
Okay.
And then the immune system comes first, and then the neural systems comes later, right? So that even amoeba can distinguish between self and non-self. But once you say self and non-self, that's more about the material self, right? Once the external you comes to interact with, then there is some rejecting response emerging.
You're saying that immune system does not have cognition, or does have cognition?
That's a very interesting question, but I cannot answer that. But the immune systems and neural systems are interacting with each other.
Yes.
Right. So, for example, once you are in a very disappointing state, and then your immune system is also getting depressed. But once you get, so people try to cheer you up, right? And then the immune system is getting better. So it's apparently there is a correlation between the activity of neural network and then the immune network.
That on our stage, or any of the mammals, or even fish or amphibians.
It's very difficult to answer to that question.
Right.
But once you have a neural network, and then the system that comes with the neural network also has an immune system, I think.
So you studied physics, and you're probably aware that in quantum physics, you have this thing called Planck time, or Planck space, Planck scale, Planck scale. So Planck scale means that when you reach the point of 10 to the minus 33 cubic centimeters, or 10 to the minus 43 seconds, time and space sort of disappears. It kind of evaporates. It loses its meaning. So 0 plus 0 plus 0 is 0, meaning there's no such thing. I mean, nothing material about these things. They're just a data structure, so to speak. So I'm promoting the idea of like, the whole world universe is a data structure. Okay, that's how I see it. So when the world is a data structure, you have like different types of data. Like data structure has like centralized data structure and a decentralized data structure. Tables, cars, chairs, rivers, those are decentralized data structures. They don't have sentience or consciousness or anything like that. Whereas centralized means like, I think all life is based on game theoretical sort of platform. So you need game. And that's why I'm very interested in like studying more about game theory. But unless you have game, there's no life. There's no life, and then if there's no life, there's no consciousness. So I always say no life, no game, no life, no life, no mind, and therefore I think that's the source of the whole world. The universe is a data structure, but the data structure happened to sort of evolve. I mean, the word evolve also involves time space, and that's why I kind of like want to stay away from that idea. I would like to rather say, time space time could be a software, and we're like using our sensory organs to gain access to these information or data structure to experience what we're experiencing. What I use is, you know what a QR code is? I'm sure you know what a QR code is. But
sure.
When you look at QR code,
was it invented by Japanese?
It was originally a barcode was invented by American, I think. And then it kind of Japan is like really good at like I think it's QR code is just a two-dimensional object, right? It's two-dimensional, but when you put a camera over it, movie pops up. You get to see videos. That is already it's kind of like a hologram situation where you get to see things, three-dimensional or two-dimensional. That's why I'm thinking that QR code is basically the whole world is like a QR code, and we have all these data structure, and we're using our organs and sensor perceptions to sort of, and then integrate them inside our brain when it comes to us to sort of navigate ourselves and experience the world. And so that's how I see the world, and that's why when you say being conscious, it always have to be about the centralized data structure, and as opposed to decentralized data structure. When you're centralized, you need, so the whole world, again, this is another theory that I'm working on actually, but time progresses, and then because you study physics, you have the second thermodynamic theory of entropy, where entropy is increasing when time progressing. That I had always had sort of feeling it didn't work. It didn't really come together for me, and I thought that accumulation of information is rather more, how do I say, it kind of explains how time progresses rather than entropy. So even if you include entropy, the more the time progresses, you are actually adding information, whether it's in entropy or not, decentralized or centralized, right? So in the end, I'm sort of like flipping the Shannon's law to understand, to remap the timeline. And I see time as sort of like a software. When we gain access to that time space software, we sort of experience, and it's an addition rather than and randomness growing. is time. And so the randomness is also incorporated in our time space. Therefore, we need to sort of navigate ourselves to sort of, I guess what happens is that some way this randomness got together and brought this, I think it has to be probability, I don't know what it is, but centralized organism or centralized data structure sort of emerged from the randomness, and then it started to collect data to benefit itself. And that's where I think probability, the mathematical understanding of probability is probably the torch or the searchlight or something that helps the centralized organizations or centralized system to sort of navigate themselves to understand how the world works,
Right.
to experience. And so anyway, so that's pretty much the broad idea that I'm like sort of
No, I didn't get I didn't understand the last part, but the rest part is something that is very much like a central theme of the theoretical physics, right? I mean, usually that people think that the time is equal to entropy, entropy production, right? It's something about time, but so your idea of taking time as a software is very interesting.
Thank you so much.
And then, do you know like a hash life?
Hash life, I heard.
A hash life is the game of life. You know, game of life.
Yeah.
The game of life is just it's a very simple rule set, like surrounded by two states, three states. But then, if you can memorize, because it's a deterministic system, right? So that once you have this pattern, then it's after 10 steps it becomes like this, right? And if you have like this pattern, then after like 20 steps, the pattern becomes like this, right? So once you experience those patterns, you know what this is going to be like, right?
Yeah, prediction, right? Yeah, prediction.
So that why don't you just taking this one as a hash and then remember everything?
Yeah.
Then so when you simulate with this memorizing computational framework, right? And then game of life start with like a normal pattern formations and generations, but gradually it is accelerated, and then covering everything, so that the time in computer can be accelerated once it is deterministic. So this hash life idea is very interesting. So that even if it's a very complex pattern, you can predict and you can simulate, like billions and billions number of generations. So that's what I think is very important for computer science and also physicists those who are interested in artificial life.
So what I was talking about when I said central and prediction model is that when you live inside the chaos of randomness, you need to sort of the game of life, or sort of like the game itself, starts right on that spot. When you're in that situation, you need to keep. In order to, I think this is homeostasis or maybe conservation. I don't know. Conservation better. I don't really like to use the word energy. It's all information to me. But conservation, I guess, in order to energy conservation, or in order to protect itself, it needs to start using prediction models to navigate itself through the randomness, and that is actually the force that emerges centralized organisms or centralized system, which later becomes life. And so even us, like our body is like, we got this what do you call this sympathetic system that actually controls us. Each organ is like separated. It's sort of like a separate creatures, so to speak. Organ. I mean, at the end of the day, your blood cells are also some sort of organism in a way. Yeah. So we're symbiotes, so to speak.
Yes,
just like
sense. Yeah, but the important thing is, I think, once you have tons of data structures and information that constitute yourself, right? But it must be instantiated in the world, and then if the bits get lost, it's going to be a big problem, right? Because you cannot maintain yourself. Right? So the question is how to maintain bits and information that is related to yourself, right? So this is all about the immune system, and then its immune network is try to repairing and then maintain information within the network, right? And those information is about you, right? So as you said, if we are we are the integration of all those information on bits, those bits must be maintained within a system, and this is by immune network that is watching which bit is repressed or which bit is getting lost, and then try to repair it. And then once the other information is coming, then how to settle those information within the system. It's something that immune network is doing, I think. Right?
So when you say bits, in computer terms, it would be tokens.
Yeah, you can say that, but bit is something like it's not just it's something that carries the information. So one bit in when you say like one bit in DNA, for example, the DNA sequence is we can say like sequence of ATGC is something right? But this one bit must be supported by energy. Otherwise, it's going to be, it collapses and then get lost. So, simply speaking, like the DNA is getting shorter, or then those molecules moving around in space so that you cannot, collect them to come to the same place to form the string. No? So I think it's so the information bits and then physical bits, or what you call it, is complementary to each other, right? That's why the physicists think what kind of physical systems supports this bit is very important. So it's not just energy; it's something it's independent from information, but because of this energy structures and system that can sustain this information, that's why this one can exist in the universe. Right? So usually the people have been discussing only about the bit, right, in the game of life. But usually those systems also run on a computer, and the computer needs energy. And then also those the molecules that constitute computer must need energy to combine them together, right? And so that the physics and information space is not separate, independent from each other. It's more like the same thing, right?
How do you observe? So conceptually, I understand that, but there's always a thin line between the two. When you say bits, and then you got the quantum qubit, or
Yeah, but once you put the water in the computer, it's just break up, right?
Yeah.
Why it goes like this? It's because the water that influence the system itself, and then it crashes every bit, right?
That is true, yeah. But water, if you have a cloud system, and the cloud is like basically electromagnetic, airwaves. That's you can rain or bring storm and wash it with water. It won't affect anything. I mean.
So I think the point is whether you can repair and then collect those bits. I mean, of course, it's in your term it can be decentralized, right? And diffusing into the space, right? But once you know where those bits are, and if you have like
central,
right, then you can bring it back to the.
That's probably
what you're saying, right?
That's what I'm saying. Yes.
Yeah,
yes.
in order to do that, then we need another information or another, space
Software,
Right,
yeah,
right. And that is almost impossible. So that's why that system is try not to become like that. So that they locally they want to self-repair and then maintain the information that you have, right? With the physical systems, I think. Well, like even von Neumann, when he wrote the self-reproduction book, and then he said, well, this is beautiful, so that self-reproduction is possible with my machine and this and this. However, once you want to bring it to the physical space, you really need to think how those, grids constructed in the real space. And he designed like fractal structures so that even if there's a noise, the noise cannot come to break easily. So this strange structures that he was talking about is probably necessary.
Yeah, so I guess we're talking about the same thing. When you say noise, entropy, randomness, that is something that in order homeostasis, or you call it conservation of energy, it needs to sort of like protect, keep the state, sort of like status quo.
Yeah.
And that's why they sort of form a system where they can kind of eradicate the entropy and neg entropy and growth and entropy, whatever they call that. So that's what you're talking about, I think.
Yeah.
Is that what you're talking about?
Yeah,
Okay. Yeah. So my question is the data structure and informatics versus the actual physical qubits and quantum. There's still sort of like a membrane or thin line that doesn't really communicate or connect, and that's my issue with
You mean qubit and normal bit? Or quantum world and
quantum world and the actual the soft information itself. How do we describe and how do we can only observe information through post de facto, like meaning like after whatever happens, that you can see the effect, but you cannot. There's no identifiable sort of like a quantum, so to speak, that is the information.
Yeah, but that's very difficult problem. I'm not sure whether I can answer properly to what you're discussing. But when I took my Ph.D. and went to Kyoto Research Institute for Fundamental Physics, I worked with Professor Kensuke Ikeda, and he was studying quantum chaos. So the quantum chaos is, what is chaos in the classical world?
Chaos,
Is okay, but what about the chaos in the quantum world? Right? And that time we don't know what this one is. Right? And then because of the Planck scale, so chaos is trying to amplify minute differences into macro scale. Right? But if there's a Planck scale and then the uncertainty principle, those differences is ambiguity, right? So you cannot amplify it, right? So that even the same Hamiltonian, same dynamical systems is classically in a classical world they can generate chaos, but the same system in a quantum world you cannot generate chaos, right? So it seems very strange that people thought, right? And Kensuke thought that was strange. So he put noise, added noise to this same quantum dynamical system. Then the chaos came up again. So that adding noise to this Hamiltonian, we call it Hamiltonian, but adding noise to the Hamiltonian, make it possible to have chaos like we see in a classical world. So that the people asking him, and then, so what is this noise? Even this is chaos, but put another noise in it, and it's so strange. And he said, well, maybe this noise is observation processes. So you really have to see, you really have to observe the system, right, to bring it, to regenerate chaos.
Us gaining access to those information is already a noise. Observation is a noise because
observation is a noise. Of course, yes.
we are the noise itself or chaos itself, and sort of trying to interact with the
Yeah.
right.
Yeah.
So okay.
So the noise and chaos was very much like a central theme when I was working when I was a graduate student. And then noise induces chaos, and then so there's a classical simple mapping system, right? Like a logistic map. Then if you add noise, and usually the people think it becomes such noisy, but it's not true. Once you put the noise, then the system becomes periodic or limit cycle. So people are so surprised, why? And then it's about the information. So information flow is usually, if the information goes always to the same direction from the small scale to the macro scale, then it's okay. If you add the noise, then noise comes to the macro bit and then becomes noisy, right? But some of the chaotic systems, information flow is not always go from the upstream to the downstream in a straight way, right? It goes back and forth, right? So once you put the noise in there, then information cannot go to the macro scale, so that it stays in a very stable system. So it's quite interesting, how the information flow is under the chaotic system determines how to responding to the noise added to the system. So that's what we know right now. So now that people are studying noise plus chaotic system, it's very it's kind of interesting, different systems. That's what people think.
Interesting, very interesting.
And then this noise, especially in the quantum system, that we take this noise as an observation, right? So this system requires us or the observer to be within the system. Otherwise, you cannot realize what we see in the real world. But that's what the transformer is all about, right? LLM, large scale.
Yeah.
Large language model.
Right.
Also,
Right.
What we see is a gigantic vector space.
Right.
And then
Suddenly it starts to that looks like life to me to some extent,
me too. Yes.
And that's how our brain works as well, right?
Yes. Well, yeah, I very much agree with you, but it's a very not so many people think in this way. Yeah, people think it's a LLM is something different, because it's a dynamical system, and the LLM is very different from our brain system, right? Our brain system has some different types of neurons, and connectivity is different.
Yeah.
However, the transformer is very much like multiplying always like random matrix to the high dimensional vector, and then generating another vector and then multiply with the random. But this is what we call random matrix, but it's not actually random in a way, because we can interpret this one as, okay, here is as you know, like LLM has a query and key, and that generates this matrix. Right? Query and key and value is this gigantic matrix, and then if you don't know this, and if you see this, it's just a very random matrix, but it's actually after you multiply it with this matrix like 100 times, then the final vector coming up from after operating 100 times of those random metrics, this vector is interpreted as what you are going to say.
So what's so when you say query and key, what is that? Synapses and neurons? How is that in our organism? How does that represent?
Yeah, that's a difficult. So, honestly speaking, I don't know. But a transformer is we know that this sentence is this world has adjectives, and an adjective is coming from here, so that organizes this matrix. But in our brain system, I don't know. So that the people are very much skeptical that okay, but this transformer is just a predicting machines, right? And it's nothing to do with the brain. But I don't think so. So that's what we still have to understand what's out there.
I'm trying to apply this, LLM transformer system to sort of apply it to people learning language. When you dump a whole bunch of words, I mean, if you're dumping a whole bunch of meaningless words, it won't mean anything. But when you dump a sort of like idioms and phrases, then it starts to kind of like starts to connect and reconnect, and then it starts to make sense. And people, I like to actually experiment this with students when we try to we try different methods, but we can compare that with it. And just dump the whole bunch of like phrases, especially learning English. You want the phrases and the idioms, and just randomly like put it in and have them memorize it, and just like leave it, and then it starts to sort of conceive. Yeah.
Do you know Elman network? So Elman network is it's not like a transformer. Transformer is always just multiplying and multiplying. So the information is always go from input to the output. But the Elman network, and also in general, recurrent neural network, is the information is recurrently in the network, right? And then the Elman is Jeffrey Elman in the United States, but he created this simple network, very simple, and it's not large like LLM, right? Yeah, 3 layers. And it's about 18 neuron or something. But even though they cannot understand language, and then once you put the sequence, and then once you look into this latent space, latent network, hidden layer, then you can see nice patterns like we see in a deep neural network of verbs and nouns.
Grammatically correct.
Right.
Whoa.
So people are so much excited about this, but you cannot scale it up, right? So, because this Elman network is, however, it's already that people think that, you cannot train this network from, begin with a gigantic corpus, right? You definitely have to gradually increasing the training size of the words, right? So this Elman network can learn it, like the kids can learn. First of all, it's like 10 words, 100 words, 1,000 words, and then
exponential.
Yeah. So that's how this the kids can come to understand how to use the language. But the LLM is different, right? Starting from a gigantic corpus,
right,
and then put it into the network, dump it into the network. Then he can learn everything. So the people say, okay, here is the developmental processes.
Yeah.
And then there is a way. However, like Chomsky says, do you know Norman Chomsky?
Yes.
Norman Chomsky says that there is a lexicon on the syntax. Lexicon is
dictionary,
right? And then syntax is a grammar, right? So these are two different things that exist in our brain, and then it's what he calls universal grammar. Even any kind of language. However, what we learn from LLM, and then before LLM there was a internet that people are correcting grammatical errors and things once somebody got into. And then also the LLM shows that the syntax is emerging from the gigantic corpus. Even if you don't know what the syntax is, which one is noun or which one is not.
Naturally.
Yeah, but naturally that you can generate and understand.
We have a universal syntax inside us. That's
what Chomsky says. However, this LLM and other Elman network shows us is that syntax is emerging from it, right? After as you said, after put large corpus into the system, then the syntax is emerging from it, and then people say, "Hey, man, there is a rule that this words must go this way or S."
I think meanings, what's called semiotics. Yeah. Meaning has vectors. It has directions, I think.
Well, that's what the transformers and we do in transformers, right?
Yeah.
Because it's what we call word to back.
Yeah.
So once I gave a book, right?
Yeah.
And I is corresponding to like a gigantic vector.
Yeah.
Right, and then each word has corresponding to the vector. Right?
Exactly. Yeah.
And then this one, it doesn't have any meaning, right? Just indexing those words.
Right.
However, after 100 times of operating with a random matrix in the transformer,
Right.
then those numbers, becomes very different because they are containing like a sentence context, right? Semantics is controlling with how I is mapping with what numbers.
Exactly. Yeah.
So this is very important. That's what transformers and those matrices is doing. Right?
Yeah.
So from the word to back to something like I just said, like semantics and like meaning space. It's something we can get it right. That's very important, and nobody could expect that this meaning space is simply acquired by multiplying this matrix, which is we call attention, right? Attention layers. So attention is so important because we can reach this meaning space from word to simple word to back space, right?
Because you were also sort of like interested in art. I kind of bring this to you because music is a language. That's how I see it. But so birds, when they chirp, they're signaling something. There's a meaning to some of the dogs barking or what, and then that turns into music. In us, we actually kind of like separated these two semiotics or what
I think so.
Yeah,
I agree.
Language, logic versus music, and music is sort of like an independent thing.
Yeah.
And so when you're like really, immersed into art and you do all kinds of, artsy things.
but because it's like, actually I went to see Eno. Did you see already?
No, Eno?
Eno is a film about the Brian Eno.
Oh, okay, Brian Eno. Yeah.
So there was a movie, the film called Eno, right? And then it's all about what it's an interview with him, right? And then Brian was saying, it's quite interesting because why he's doing this, and then because he's interested in generative systems, right? And then generative back in 1980s, generative by using those synthesizer from things and things. But now that you have like transformers and everything, right? But it's all about generative systems, right? And then he's interested in music, and then because of this, using the generative systems, and then he talked about the game of life. Okay, there's bits, and then if you flip this bit, and then it's diffusing into the space, and this is what he's very much excited about. And also he showed like a double pendulum, which is chaos, right? How these simple systems can generate what you cannot expect. So this is his motivation was using all ideas in music. But he didn't say that explicitly. But I was very much sympathetic with why. So when I'm explaining what I'm doing with the artist, and okay, here's the chaos system, here's the automatic game of life, and these are the generative systems, right? Even if it's empty, it's very simple initial configurations, but it still can generate very complex patterns, which is unpredictable.
Right.
Right. So it's a computationally irreducible. Those patterns, we don't know what kind of pattern is generated from this simple initial configuration without actually simulating this pattern. Right? So that's what we say. That's what we call well, I think it's first guy. He was Stephen Wolfram. He was saying that this is a computationally irreducible. So that you do have to compute it, right? So that's what generative system is about. And Brian Eno is the best person. He's translating all these complex mathematical theory into art and music. Yes.
Wow.
So I really like him.
Interesting.
Well, I've never met him. I mean,
no, never. But yeah, he was famous during the 80s and 90s, right?
Oh yeah,
Yeah.
And then he has a very interesting conversation with the scientists and artists.
Right.
Yeah,
Interesting guy.
yeah, it's interesting guy. Yeah.
Maybe we should interview him at one point. Yeah.
He's very interesting. Yeah.
Yeah. Okay.
Although he has a very peculiar. I think he's interested every day. He doesn't have anything to do. That's what he's saying. And then he started to push the button or write something, and then from there that he started to do some complex things coming up with. But he definitely enjoyed his life. Right? And usually now I remember that he said, so usually he also, when you get up, look into the iPhones and emails and start to get more information from outside, right? That's his day. I think almost all the people, right? Starting every day by getting information from outside.
Yeah.
But then he stopped it. So he started meditating things, walking around, so that not information is coming, but his information is coming out from his internal state, right? Because he has to write down what he thinks and his music and his patterns and drawings and so it's not getting information, but it's out information. Right? So I think so that he said that we everybody has to don't read emails.
That's what. Yeah, exactly.
Yeah, exactly, right.
Yeah.
No, I really like. That's why I really like New Mexico, Los Alamos and Santa Fe.
When was that? You went there like a while ago.
It was a while ago. It's 1990 or 86.
Right.
And then have you been to New Mexico?
No, never.
Did you see the film called Breaking Bad?
Yeah. That's Albuquerque, right?
Yeah. I'm so much the Breaking Bad is such a
it's a huge it's a big hit. Yeah, it's like Pinkman and
Pinkman and
Heisenberg.
Yes. And then Breaking Bad tour. Do you know this?
Oh no, I haven't. Have you participated?
Yeah, because I told my daughter also became a big fan of.
Oh really?
Yeah.
Okay.
So we together.
You went to? Did you meet Brian Cranston?
No.
I met him actually once.
Oh, really?
Yeah.
Wow.
He was in.
Congratulations.
He was in Godzilla, the very first.
Really?
It was the second Godzilla that was made at Hollywood, but it was like it was a collaboration between Toho and I think it was like Legendary Pictures. And he was at the opening and the red carpet, and we actually he was like sort of sitting next to me.
Nice.
Yeah.
So the tour was very nice, and then we went to this car washing shop.
Oh, you did really? What about the camper? The camper?
Of course.
Yeah, you went inside the camper.
Tour was with this camping car.
Oh my God, that's so.
And then we went to the house where the pizza is on the roof.
Oh gosh.
But anyway, so.
How much did you pay for that? That's a
I
lot.
forgot. Yeah, that's a lot. But what was such a worth doing this?
Okay,
so
you and your daughter.
Yeah, right. Yeah, my daughter was a high school student then. Anyway.
Okay. Yeah.
I was nice.
Yeah, that's funny.
Yeah.
Okay, well,
I'm sorry, but
no, it's really been great. I really enjoyed it, and maybe lastly we can ask you about. I just want to ask you about A-Life. Why are you working on A-Life, and what do you expect from A-Life?
That's exactly what I have to. So AI is about optimization, right? Optimizing everything, right? For given task or given function, right? But biological systems, people say it's an adaptive system, right? So that people think, okay, this adaptive system is also optimizing some things, right? But the point is, AI is optimizing the given program. However, the biological system, I think, is optimizing towards the future, because the biological system is not. It should not, too much tune to the current problem, because there is an evolution time scales, right? So always have to think about what comes next. What
Prediction.
Yeah, predictions. Yeah, kind of prediction, unconscious prediction, right? So it's optimizing toward the future. So it's currently it's not optimized that people think it's well it can optimize. This is not efficient enough, right? Of course, so bring it to the lab, right? Then you can optimize like enzymes and things in very more efficient things. Right? However, after 100 years, this thing is not optimized thing, right? But the ones what you found in a wildlife becomes more better than
Because of the evolution?
because of the evolution, right? But he knows that the future is something like this. It's always optimizing for the future, not the current problem. So I think that's what the biological system, artificial life, what we have to think about. Artificial life is all about predicting the future, and they're not optimizing the current state. But it's all about what's out there in the future. So it's all about this a timeline.
That's what you call open-ended evolution.
Yes.
Yeah. I think artificial intelligence actually is going to take over the organisms that we are in the very near future, so to speak. And not some people talk about cyborgs, but now the fact that we are handing over the torch of evolution, because the randomness,
Maybe.
you know what I mean, like the randomness of
sure.
So eventually AI is going to
Take over.
and then we're kind of like obsolete to some extent, but we will exist because AI needs data structures. We are going to be the data farm for AI exponentially. Even if they go exponential, they will still need to gain access to our randomness, so to speak, that we carry. So they will cherish it. We will become the farm, the data farm.
Data farms,
right? Yes, that's pretty much what I see.
Yeah, that's very interesting idea. That's nice. Yeah, so it's in that way, I think it's very that reminds me of what I did in 2010, because in 2010 I made a strange machine called mind time machine. It's a mind
time machine.
No, it's a mind time machine.
Mind time machine.
So I think mind has its own time axis, right? And then it's not a real physical time, so that I need to understand what is mind time, right?
Locality.
Yeah, and then also the time is not always go to that direction.
No.
But it's like mind is like post-predictions and predictions, post-predictions. Even if the future event that masks what we see in the past, which is very strange, right? Time is goes back and forth. So I try to simulate, or I try to make a machine that has this kind of character. Right? So that was, that before the deep learning came out, so that the bunch of neural network, but it's not so, smart as deep learning system. But we made a large, 3 screens and neural network behind it. So once you captured on the screen, then he remembers it, and then sometimes he cast on the screen so that he can more remember. So that I was so much happy with this, and I put from the spring to the summer in the Wycombe, in the museum, right? I don't know why this machine, because this machine is more like art stuff. But then there's a slow time scale, like from the spring to summer, and also a very fast time scale, so the neural states. And also people are coming every day, so it's like a middle time scale. So different time scales is I think it's very important to generate conscious state or mind time. So that was, then I somehow I thought, okay, I really have to explain this machine to people in Google. Right, because I think Google research people should understand what I'm doing. Right, so I went to the headquarters and asked them, "Can I give a talk there?" And they said, "Oh, yes." And I went there, right, and Ocean View, right. then I explain, what the mental machine is. But people don't understand what this guy is talking. However, after that, then just Google, Gmails and things came out. So that then I talked with the engineers, right? And then they, well, we're not so much interested in consciousness, but we took care about Gmail, how to maintain Gmails without losing information for 24 hours, 365 days. So we have five or six data storage center, and then hidden in
underneath the campus, right?
Yeah. Then in order to maintain this Gmails and Google Docs and also Google searches, right? They have to create like a pager, is a simple system, and then Hadoop, and then MapReduce, and all these systems. But this new algorithm they have to create only because they want to maintain this information without losing the bits, right? So I was listening to it and said, hey, wait, so these five or six techniques that they invented is very much similar to what our brain system created. So it's like it's very interesting, like memories and conscious state and all these, the reading out memories. So I think, okay, don't think, mimic our brain system, but like maintaining, this, information system without losing bits. Then we have to create those algorithms, right? And this artificial system is more, akin to brain system. So that's why it was so much, I feel like I understood. I felt, finally I understood what engineering people are doing, right? Because this system, they don't understand consciousness. They don't like, brain system. However, but as a result, what they made was the best model for our consciousness and brain. So I was so much, happy with understand this one. So I call it, it's a Hadoop brain or something. I tried to, I got the grant for it, but then I call it Hadoop brain. It's something like that. It's nothing to do with our connection, our architecture in our real brain. However, this algorithm called Hadoop and then MapReducing system is very much effective, sending information and getting information. And then our brain is all about, like you said, a gigantic data center.
Centralized structure. Right.
That's why, and I thought about, that's what I run from Google.
Oh, okay. Then did they credit you for helping them build that system? They should. I mean, you should get paid for that. I mean,
but that's quite nice. And then after that, I got interested in web systems, the internet, because the internet must be centralizing data.
Yeah.
And even if nobody touches internet, but still they can they can survive for years and years. And their autonomous system is moving around, and those algorithms and processes that Google created that exist in the internet. So the internet itself is like a brain or the living system, right? It's artificial life.
It is.
So if this complex artificial system doesn't become life, then we're never gonna make artificial life.
Yeah, you're right. Yeah. Absolutely.
So that's why I got interested in web systems, and then I was thinking that maybe making a large system that may change, comparing with a small system, large, even if the algorithm is the same. But because the data goes beyond some threshold, the systems become different. So that's why I simulated like billions of voice words, and how those gigantic information streams becomes lifelike, and that's what I have been doing. Then the transformer came out, so I thought, here you go,
You're almost there, right?
So that's why I'm here. I mean that's why I'm interested in making like a large system, the information flows, and that is what we have to understand.
All of these systems are sort of like a supporting interface system for us, our brain.
Yeah.
So convenience is the meaning of what it.
Yeah.
So I guess convenience is the mother of consciousness. Building a system similar to
You mean the interface?
interface. Yes,
Yeah.
interface. Yeah. So we are, because it is the mother of, like, if it's convenient for our brain or a consciousness, it develops into something independent and original. And
Yeah, well, I don't know whether I still don't get to the point whether the interface is important, but what I found was, in order to, as I said, sustain information and data is what our brain is also doing, and then try to regulate information flow in a system. It's something our brain is doing, and also what. So those things must be much more important than understanding, life.
Yeah.
Maybe.
We accidentally built life without knowing.
That's right. That's exactly the
yeah.
point. Yes.
Well, Professor Ikegami, thank you very much for your time.
Thank you so much.
It was a great pleasure having you. Thank you so
Thank
much.
you so much.
Thank you.